So good morning. It is terribly early. I'm on autopilot, so there are a few things that I want to remind you from Monday. Monday I presented some of the applications, say in speech processing, wireless communications, that use Gabor Frames, and I've presented just the bare structures that lead to the mathematical concepts of Gabor Frames. From now on, it's the mathematics, what we know and what we don't know. And before we start, I want to remind you of what we did so far. So, lecture 1 was Gabor systems in signal processing. Today, chapter on course structure, probably that will prolong itself until tomorrow. So, important is that throughout these 4 lectures you keep in mind notation. Translation by x is just shifting the graph of a function. Good morning. So, shifting function by x. Modulation, multiplication by complex exponential. We have seen that amounts to a frequency shift. And then from now on we simplify further. We combine time frequency shifts into one operator. So modulation, translation. I write it in this order. Also, well, it's time frequency shifts, but for most applications it's more advantageous to write modulation before translation. So combining these in time and frequency into one point in time frequency space, one point z, we have time frequency shifts. So these are the main objects. Here you have a graphical illustration. Shift modulation amounts by adding oscillation, a controlled wave combination. So then we looked at certain sets of time frequency shifts that are labeled by a lattice. A lattice is essentially the integer lattice z2d in time frequency space, and then it's deformed linearly by an invertible 2d by 2d matrix. And the set of all time frequency shifts generated by such a lattice is a Gabor system. In the applications we just had translation by multiples of some parameter alpha, modulation by multiples, integer multiples of some parameter beta, and so we looked at the rectangular lattice. For the general theory I will use arbitrary lattices, but in the applications you saw lattices parameterized by a time shift and by a frequency shift. So then we saw that for, say, speech processing, signal segmentation plus Fourier series, we needed Gabor frames. So essentially we sample f, or we take correlation with time frequency shift along the lattice lambda, take the discrete L2 sum, and you talk about a frame, a Gabor frame, if this discrete L2 sum is equivalent to the L2 norm of f. We've seen that the underlying operator is the frame operator, and this inequality is equivalent to saying that the frame operator is invertible. And once you have that, you can reconstruct from the knowledge of these coefficients in a stable way. So the dual concept is the one of a resequence that appeared in wireless communications, where the coefficients c sub lambda are information that you want to transmit, and you create an analog signal by taking these coefficients as coefficients of a Gabor series, and that's the analog signal that's being transmitted. For decoding at the receiver, you need some conditions, and that's condition of resequence. You require that this series, so that's now a function in L2. The 2 norm is equivalent to the 2 norm of the coefficients. Then you have a stable reconstruction by means of the Gramian So another object related to Gabor system is the grammene. So this matrix here. Let's see what else. Okay, we don't need this. Okay. So today we start with the mathematical problems. So we want to know when, under which conditions on the pulse, on the lattice, do we have a Gabor frame or a Gabor Riesz sequence. And these are questions that post themselves immediately when we looked at the applications. We saw that you cannot construct a pulse that's with compact support in time and frequency. And so that's the ideal, but you cannot do that. So the question is already what kind of windows, pulses are suitable, what kinds of lattices. Today I will give you some characterizations of Gabor frames that give us some tests. How do we check that a Gabor system is a frame? Starting tomorrow, we look at examples, how to construct and what might be abstractions to the frame property. Okay, relevance and relations, I have indicated some of that in the lecture on Monday. There are many more relations to other fields, quantum mechanics, complex analysis, harmonic analysis, and so on. I've not touched this again. So I think, okay, that's it for today. So escape. The rest will be on the blackboard. Yeah, I would like to. So he's gone. So how do you? Well, whatever. So I strongly believe that the only pace to follow mathematics is on the blackboard. But I realize that this lecture room is not appropriate for blackboard talks. So in the back of the room, you have to stand up or use magnifying glasses, or I try to write a little bit larger. So question is, given a window, a pulse G in L2, a lattice lambda, and lambda is obtained from the integer lattice by some invertible linear transformation, how do we determine whether this is a frame or not? Before doing that, I need a second lattice associated to this. That's the so-called adjoint lattice. So for that, we introduce a matrix consisting of blocks, block matrix. So this is a 2D by 2D matrix, and these are D by D blocks. One would say this is the matrix that describes the standard symplectic form and has lots of words. I omit those. And then the so-called adjoint lattice is a lattice generated by the following matrix, a symplectic matrix. Then we take A transpose inverse applied to Z 2D. So this adjoint lattice has a mathematical meaning. For us, it will just drop out from the proofs. But essentially, and that may be something you want to think about, all time frequency shifts belonging to the adjoint lattice commute with all time frequency shifts in the original lattice. So in a way, this lattice describes the commutant of this lattice. So, okay. So now comes, I would say, the fundamental description of Gabor frames. And my goal and ambition for today is to give you or indicate a proof, a more or less complete proof. So this goes back to, I think the first one was Janssen for rectangular lattices, Ron and Shen for rectangular lattices, and then for arbitrary lattices was Feichtinger and Kotzek. So 95, 97, actually one of the few publications in a highly regarded general journal, Duke. It's not that easy to get applied stuff into the general journals. And this, I think, is in the second book on Gabor analysis, edited by Hans Feichtinger and Thomas Stromer. So G in L2, non-zero, and then the statement is following. The following conditions are equivalent. 1, the Gabor system, so the set of all time frequency shifts along the lattice lambda is a frame. Two, the Gabor system belonging to the adjoint lattice is a Riesz sequence. And 3, for that I need one more definition attached to lattices. The volume of a lattice is the absolute value of the determinant generating this lattice. Lattice may be generated by many different matrices corresponding to different choices of a basis, but the volume is independent of a lattice. So if you look at the rectangular lattice, so here is alpha, here is beta, then so simply the smallest, the volume, or in this case the area of the smallest parallelogram in the lattice. Alternatively, the inverse of this, the inverse 1 over volume is the density, the average number of points per unit volume. So third condition, that's the so-called biorthogonality condition. There exists a gamma in L2 satisfying an upper frame bound. So the word is Bessel. I will not deal on that. Such that we have the following biorthogonality. So a normalizing factor, which is essential, gamma, and then pi mu, inner product of gamma, with pi mu of G is equal to delta mu 0, and that's for all mu in the adjoint lattice. So 3 conditions, equivalent, frame, that's what we want to understand. The main assertion is that the frame property and the Riesz sequence property are dual to each other. When you switch from the adjoint lattice, from the lattice to the adjoint lattice. So if you, yeah? What is Bessel? This means that the Gabor system has an upper frame bound. Or you could say the corresponding frame operator is bounded. This is a detail that I'll omit in the proofs. So you have to be very clever to construct windows that are not Bessel. So this is, if you are interested in pathologies, you will deal on that, but it's not the main point here. So the corresponding frame operator with this window, and let's say this lattice. Yes. Do I need to say more? Yeah? Pardon? That's a Kronecker delta. So it's one. You get 1. If the inner product of G, gamma with G, normalized is 1, all other inner products are 0. I tried to say it. and I try to emphasize this if we are interested in whether everything is well defined, then surely do I need? No, I don't want to do that. The frame operator corresponding to the adjoint lattice is bounded. So unless you have to try hard to find windows that don't have this property. So, okay. So the volume of the adjoint lattice is, let's see, is determinant A inverse. So on a very, very coarse level, you can understand this duality the following way. Frame, so means that this system spans the space. Finite linear combinations are dense, and so you need sufficiently many vectors. So this should mean that the volume of the lattice is relatively small. Riesz sequence means that you have linear independence, in whatever sense, of the corresponding time frequency shifts. So in this case, I never said anything about spanning. They just are linearly independent, span some subspace. And in this case, you should have relatively few vectors, or the distribution of the lattice is relatively coarse. And what you see here, if the volume is small, then the volume of the adjoint lattice is large. So qualitatively, this is about right. Also, when you look at the definitions, in one case you take inner products with functions in L2 and get an equivalent norm in little l2. Here take linear combinations with coefficients in little l2 and get norm equivalence. So in a way, so this is sort of a rough intuitive understanding where where exactly the adjoint lattice comes in. I'll try to show you. So I would like to spend, well, 40 minutes may or may not be enough to show you a proof of this. I mean, there are about a dozen or 2 dozens of characterization of Gabor frames, and they have been derived independently from scratch in many papers, but one can derive basically all characterizations that I know from this duality theorem. Probably I'll give you one example tomorrow. So, proof, and here I ask your attention. I will give a proof, but I'll omit technical details. So questions, when is this defined? So basically I give you a proof and you have to find the conditions on G that you need. So I'm going to cheat and you will tell me when. Okay? So, so when we look at, once again, frame means that this sum should be comparable to the 2 norm of f. Okay? So we are interested in estimating this sum of inner products. So the function that we are looking at is essentially, let's call it h of z. That's the absolute value of f with pi z of g. So instead of just evaluating the lattice, we take inner products with all time frequency shifts, and we study this function. So when you look at this, and spell it out, then this is integral f of t. Here we have modulation. Say, let's write z equals x psi. So we have modulation by psi and translation by x That's a well-known object. Essentially, it's the continuous analog of these inner products, or of our original motivation. You take f, truncate to a neighborhood of x, and take Fourier transform. So this is the short time Fourier transform. I will abbreviate that by f. So inner product of f with time frequency shifts at time frequency shift z is the short time Fourier transform. And taking the absolute value squared also has a name in engineering. That's the so-called spectrogram. Essentially, delete phase and just look at the amplitudes squared, interpreted as energy density or whatever. So essentially, that's the magnitude of the amplitude squared of the signal f at time g at frequency psi. That's an interpretation of this function here. Okay, and now basically what we have to estimate, or what we have to understand, is this expression, some h of lambda, where lambda runs through a lattice. So with a minimum of harmonic analysis, there's a clear instruction what to do when you see a sum of a function over evaluated on a lattice. Let's see. So you want to see that at least once, right? So that is Poisson summation formula. So the Poisson summation formula says, so f, well, okay, suitable. So say in Schwartz class, there are many more conditions that you could, many weaker conditions that you can impose. I'll say a little bit about that probably. Then the sum fk, k in z, well, in this case we have 2d, is equal to sum f hat k, k in z2d, and this is the Fourier transform with the 2 pi in the exponent. So that's a fun, so that's okay. Okay, and here, essentially we have sum over z2d of h, a, k. So I don't want to worry too much about all these transformations. So I write down the Poisson summation formula in this sense. And so there are many conditions under which this identity holds pointwise. And in the course of the proof, we just have to make sure that we can apply Poisson summation formula. Okay, so we are interested in this particular function, the spectrogram of f with respect to a fixed window G and a lattice. And the very form of this sum suggests that we apply Poisson summation formula. Okay, so when you look at this function here, first question we have to answer is, what is the Fourier transform of this here? So what is h hat when h is the spectrogram? So that requires some work, and I want to, well, okay. so this is, if we have understood how to compute the Fourier transform of the spectrogram, then we are in business. Then we can apply Poisson summation formula and see what happens on this side. And OK, so this is a sequence of small lemmata. Could call it the gymnastics of time frequency shifts. So the first is so far I haven't done any calculation, so it's time that we do something. So time frequency shift by z inverse, time frequency shift by z, time frequency shift by zeta is equal to, and well, this I'll never get right. So this is e to the minus 2 pi I. Then we have inner product of z with symplectic form is still there, zeta pi of z. Okay, that's a formula telling us how different time frequency shifts commute, so z and zeta in R2D. And the second one, so please sort of, it occurs for the first time here, but this, so the inner product of f with arbitrary time frequency shifts is the short time Fourier transform. So usually you fix g and look at this as a transform of f. Function of d variables goes to a function of 2d variables. And short time Fourier transform is quite indicative of the meaning of this. So the second formula that follows immediately from these commutation relations is that if you take the short time Fourier transform with respect to a shifted window of the shifted function f at z, then that's equal to, again, sign is important. OK, well, this case can remind you of what that is. It's the inner product of this function with a shift by z of this function. So you bring this over. These are unitary. Well, you bring this over, unitary, so you have pi zeta inverse here. And then you can apply this formula. So if you bring the time frequency shift to this side, then you have this combination of time frequency shifts in this position. So where, and then I bring out this factor, so it's e to the 2 pi I z j of zeta. Then you have f inner product pi z g. So e to the 2 pi I z j zeta. So essentially, if you shift both window and the function, then nothing changes. You obtain a phase factor. Phase factor in a very, but the phase factor is essential. Phase factor is a complex exponential. And so 2 follows from 1, just different notation. I think I should do this at least once. First of all, you should see where the symplectic matrix comes in. In a way, these commutation relations lie at the heart of time frequency analysis. So at least once we should do this calculation. It's banal, but I think it's banal, and you have to spend those 2 minutes in order to really appreciate this. And actually, in the further development, you can sort of build up big words around this phase factor. Okay. symplectic representation theory, Heisenberg group, and so on. So there's no end in abstract words, but underlying this is a banal observation about how time frequency shifts commute. So let's take a shift and a modulation of t, and let's try to see what happens when we change these two. So this is modulation by t, f of t, and then so this is writing down the modulation, and then we shift by u. So I have t minus u, f of t minus u. So this part does not depend on t, so it's e to the minus 2 pi I eta u. And then I have modulation here, write it first, and then translation here applied to f of t. Okay, once I pull out the phase factor, I just have an e to the 2 pi I eta t of this function. So it's a modulation by eta of the shift. So when you commute modulation and translation, you still get a time modulation translation, but with a phase factor. And it's kind of surprising that, well, not surprising, but fact that it makes the mathematics of time frequency shifts interesting. Shift operator, modulation are, say, the fundamental operations in the Fourier analysis on R, on RD, and yet there is immediately some non-commutative structure behind. So now let's look at this product of time frequency shifts. Massimo, you are worried? You're not? Checking whether people in the last row can see. Okay, so now I split the zeta and the z in the two variables time and frequency. So here we have modulation by z2, translation by z1. Here I have modulation by zeta 2, translation by zeta 1, and the inverse is translation by minus zeta 1, modulation by minus zeta 2. Okay. So I want to write this as a single time frequency shift. I need to commute through these two, okay? So if I interchange these two, then I get a phase factor. It's the product of these two with a minus sign, so it's e to the minus 2 pi I z1 zeta 2. Yeah. Then we have, so now the m zeta 2 is here, and we have m minus zeta 2 z2 zeta 2. Well, if you multiply these complex exponentials, the corresponding coefficients add. So m minus zeta 2, mz2, m zeta 2 is mz2. Okay, so product of these two, z2, I still have the t negative zeta 1 here. And after commuting through, I have t zeta 1 plus z1. So do that process once more. Commute this through. So this gives e to the minus 2 pi I z1 zeta 2 from before. Here I get, okay, now I have minus zeta 1 z2, so this would be z2 zeta 1, okay? So in total you get a plus sign here, and okay, fine. And then I have mz2, and after commuting through the translation. I have translation by negative zeta 1 plus z1 plus zeta 1. So that's this here. So here I have time frequency shift by z. And let's see. If I write this correctly, this should be exactly the symplectic form. So z1, 1, 0, identity minus identity 0, zeta 1, zeta 2. Okay. So you get zeta 2, z1, and here minus zeta 1, z2. So this is e to the minus 2 pi I z symplectic form, symplectic matrix zeta. So you may take a little bit more time to do this, but in a way the commutation relations between time frequency shifts are fundamental. And if you do it 5 times, you'll get different signs, I guarantee you. So that's the gymnastics of time frequency shifts. Now the next lemma is known as the orthogonality relations of short time Fourier transform. So all functions. So let's see, what do I have? F, G, H, gamma R in L2 of R D. And then we have the inner product of the short time Fourier transform of F with respect to G, still up here, with, let's see, short time Fourier transform of H with respect to gamma. So these are two functions of 2D variables. So L2 of R2D is equal to, so two functions in 2D variables. Try to calculate the inner product, and the inner product is inner product of F and G. This is an inner product in L2 of RD. And let's see, so linear, conjugate linear. So here it's conjugate linear, linear. So how do I write that best? So G, gamma, complex conjugate, again, inner product in L2 of R. So this says a bit more than is written here. This says in particular, well, if you take F equal H, G equal gamma, that a short time Fourier transform of two functions in L2 is in L2 of twice as many variables. Okay, so time to open the windows and take a breath. Wait. Okay.
It's very personal.
I have a different, very personal opinion.
Okay, very good.
I mean, everything I...
You can buy the book of Gabor Frames.
Well, somebody could help with a new edition. No, I think writing distracts, or at least writing would distract me from following. So I would opt for just watching. Even though this is blackboard and therefore very slow, it may be too fast sometimes. So that's up to you to judge. But I don't think there's any chance to follow these changing of order of time frequency shifts with slides. It's even faster.
Well, nowadays,
And yeah.
take pictures as well.
Well, if I don't start it too much, I can watch myself at YouTube, and perhaps you too. So, proof of this, and essentially it's Plancherel theorem. But for that, let me write down the short time Fourier transform. Then now let's write x psi again. Integral f of t, g of t minus x bar, in case, okay, so you might have corrected me, e to the minus 2 pi I psi t dt. Let's see how this is built. Essentially, I take f of t, g of x, okay? So, in g bar of x. In mathematical terminology, that would be the tensor product of two functions. Okay? Then, what I do is I make a linear transformation. The pair tx goes to t in the first variable and t minus x in the second variable. So if you compose, if you do a linear transformation here, that induces a linear transformation on the corresponding functions. So essentially what's written here is this here at tx, and that's simply by definition f tensor g bar at t minus x. Okay, so that takes care of this. And what I do after that, I take a Fourier transform in the first variable. Okay, so then I take a Fourier transform in the in t, so that would be the first variable. So, from an abstract point of view, I can read this formula for the short time Fourier transform as taking the tensor product of f with the window, applying a linear transformation to the two variables, and then taking a partial Fourier transform in one coordinate. And now basically you see that this integral is defined for suitable functions, say in LP, LQ. Here could actually take tempered distributions or whatever you like, and apply these transformations. So if you take tempered distributions, you get a tempered distribution here. So that's the beauty of this formal way of writing the short time Fourier transform. Okay, now let's take inner product of two short time Fourier transform. So that is Fourier transform in first variable, coordinate transform f tensor g bar in a product with short time Fourier transform of h with respect to gamma. So partial Fourier transform, coordinate transform, and then we have h tensor gamma bar. Now, well, so this is purely formal, but the Fourier transform is unitary according to Plancherel theorem. If we fix one of the variables, then it's unitary in the other variable. So this is a unitary operator. We can delete it. So now if you look at this coordinate transform, has determinant 1. So again, if you do the corresponding calculation, the t on L2 is also unitary. So you can also omit it. So these are unitary operators. I can omit them. And now I have the inner product of two tensors. So this would be f of t, g bar of x, h of t, gamma bar of x. And you integrate over t and x. So integration over t gives integral of ft h bar of t. So this gives you fh. Integral over x gives you the inner product of g bar with gamma bar. So that's g gamma inner product. Well, these are then in L2 of R. So that's the shortest proof. If you look at, say, other proofs, they're all based on Plancherel theorem, but using this kind of notation makes it a matter of essentially two lines. Okay, so these are the orthogonality relations. Fact is the short time Fourier transform of two L2 functions is again L2, and the inner product is related to the inner product of the components. So next and last lemma. Gives us an answer to the first question. Remember, we had the spectrogram. When we look at the frame condition, we have the spectrogram sampled on a lattice, and we want to apply Poisson summation formula. So we need to know what's the Fourier transform of a spectrogram. Here is the answer, slightly more general. So again, everything is in L2. So I take the product of two short time Fourier transforms and take the Fourier transform at zeta. This is so again, you pair the functions and you pair the windows. So this gives okay, I'll just write it. This here, and then V, F, H, J, zeta bar. So currently that's only a formula, but if you set F, so if you set H equal F, gamma equal G, then you have the Fourier transform of the spectrogram as we need it. So proof. So lemma 1 is not here anymore. So when you take the Fourier transform of something, we have an e to the minus pi, so e to the minus 2 pi I zeta z. And we take this function here. Okay? That's what's going to appear in when we calculate the Fourier transform. It's this function times e to the minus 2 pi I zeta z. I omit the complex conjugation for a moment, but Okay, lemma 1 is gone. So let me introduce here, so z zeta. Let me introduce, instead of having the identity here, I write minus j squared. Okay, and then lemma 1. So here it's good to have slides where you can go back. Lemma 1 said that this here is equal to e to the minus 2 pi I. So I don't know that by heart. Z, J, zeta, VGF, Z. So that's lemma 1. So according to lemma 1, this is therefore the short time Fourier transform with respect to minus j zeta gamma of pi minus j zeta h at z. Okay, just plug in, and here I remove a j, so what's here is minus j zeta. Okay, so that's from lemma 1, and now we calculate the Fourier transform of this here. So I'll continue. So this is integral VGF of z, V gamma h of z bar. Then I have an e to the minus 2 pi I z zeta. I write that under the complex conjugation. So z zeta. This is something we have just calculated. So the trick is, you recognize this is a modulation of the short time Fourier transform, but now of a function of 2D variables. So this is a modulation on R2D, and I can write that, I can relate that to time frequency shifts on RD. That's sort of the essence or the meaning of this formula. Okay, so let's plug in this. So this is integral Vf of z. And then here we have, okay, V pi minus j zeta gamma pi minus j zeta h of z dz complex conjugate. Okay, now we are in business. This is an inner product of a short time Fourier transform with another short time Fourier transform. And therefore, the orthogonality relations tell us this is the inner product of f with this here. I write that in the, okay, so this is the inner product of f with pi minus j zeta h, and the inner product of g with this here complex conjugate. Okay, inner product of g with this here pi minus j z gamma complex conjugate. Now, how do I end up with this formula? So I bring this over. This gives up to a phase factor exactly what's here. So if I bring this over, then I have inner product of h with a time frequency shift of f, and I switch. So this is then exactly what's written here, and I want it in this order. And if I bring this over, get the same phase factor complex conjugate, so they cancel, and then I have the short time Fourier transform of, so I want G to be the window, so of gamma with respect to G at J. Anyone wants to correct me? No? So I have to do that myself. Okay, so that, okay, coincides. So lemma 3 is done. And now we are in business. Now we can calculate, now we can apply Poisson summation formula. So now let us apply the Poisson summation formula to this function here. And on the lattice. So let's see, there's one more remark I think I need. So we take the periodization of this function on the lattice. So we have sum VFG AK V gamma H AK bar K in ZD. Okay, I think we need some fresh air. Just one more remark. If you have f of z equal h of az, then the Fourier transform of the dilated version is determinant A inverse times h hat at A transpose inverse, let's write zeta here, zeta, okay? So I want to apply the Fourier transform over the integer lattice, but then I have to deal with the dilations here, and Fourier transform of a dilation behaves this way. So when I apply Fourier transform, here I can take the integer lattice. So no open window. Okay, so according to this here, this would be determinant A inverse sum F hat of A transpose inverse K. K again in Z2D. So that's Fourier transform, Poisson summation formula applied to this function on the lattice. So now let's plug in the lemma 3. So this is determinant A inverse sum over K in Z2D. And now we plug in up there, second line. So that's V, G, gamma, J, and then we have A transpose inverse of K. Okay, just plug in K here and use, so instead of zeta, I plug in this here, and then VFH J A transpose inverse K, complex conjugate. So, one more observation. This is how I defined the adjoint lattice. It's the integer lattice linearly transformed by AT inverse and by the symplectic matrix. So this is in fact, and this is the volume of lambda inverse, and this sum is in fact over mu in the adjoint lattice by definition of V G gamma mu V F H mu bar. So now the calculations are done. Should just highlight this identity. That's often called the fundamental identity of Gabor analysis. It's a link between let's say frame expression on the lattice and some expression on the adjoint lattice. And I should also say that this way to approach it is due to Feichtinger and Luev about 2002-03. At this point I might stop for a second and ask, where did I cheat?
You didn't know that the transformation formula always for the function.
Okay, so that's one thing we have to check technically. When are we able to apply Poisson summation formula? Well, ultimately, so the point of Franz Luev and Hans Feichtinger was that there's a special canonical space in harmonic analysis, modulation space M1, for which Poisson summation formula always works. But essentially, this is L2, this is L2, so the product is in L1. It's continuous, actually, locally it's in the Fourier algebra. So this is almost enough to guarantee that, well, to guarantee that this sum converges absolutely. Likewise, L2 continuous locally in Fourier algebra. So again, this converges absolutely. And here you have to invest some more technical work to justify this is always true. If you choose, well, Schwartz function, your favorite space with a little bit of smoothness and decay, then this works. But this is where I cheated. So now I have about half a page and maybe not. Now let's come to the proof of the duality. I think it should almost be possible. So the statement to prove is the Gabor system with window G and lattice lambda is a frame if and only if the Gabor system over the adjoint lattice lambda naught is a Riesz sequence if and only if there exists a dual window. So I'll show you the biorthogonality. So assume that this Gabor system is a frame. And then the frame operator is invertible. And we have already seen in the reconstruction from the frame coefficients, it can be written down with a dual window or set. This is well defined. That's where the frame assumption comes in. And now I write the reconstruction. Okay. This is true for all f in L2. And essentially, I haven't written anything new. This is just comes from the fact and rewriting the assumption that this Gabor system is a frame. I have a stable reconstruction. Again, you might want to think about how these sums converge. So first step, let's take inner products on both sides. So this means that inner product of f with an arbitrary h is equal to sum. Then we have short time Fourier transform of f with respect to g evaluated at lambda. And here we have short time Fourier transform of gamma of h with respect to gamma evaluated at lambda bar. Okay, here is the formula. We have this left-hand side, and now I plug in the right-hand side of the fundamental identity. So this is according to the fundamental identity is equal to determinant A inverse, or well, we want the volume directly, volume of lambda inverse, sum. Well, and here it is. The sum goes over the adjoint lattice. And now let me write this in terms of inner products. Well, we can leave this as it is. So V, G, gamma, mu. And I write this as an inner product. That is the inner product of H with a time frequency shift pi mu of F complex conjugate. So this is H pi mu F complex conjugate. I switch the order, so this is pi mu F H without complex conjugate. So this is true for all H in L2. This means we can, so this is true for all H in L2, so we can drop it. And I obtain that F equals this sum here. This is true for all F. So let's omit the F. So if you omit the F, what's here is the identity operator is equal to volume lambda inverse. And here we have sum over mu in the adjoint lattice. Okay, this is gamma pi mu g time frequency shift. So I go from a weak version that's provided by the fundamental identity to a strong version to an operator version. Okay, so now we're almost done. I represent the identity operator as a linear combination, infinite linear combination of time frequency shifts. What's the conclusion? The conclusion is, well, there's a little step missing. It's one line. Time time frequency shift as operator are linearly independent. So this means these coefficients must be 0 unless mu is equal to 0. So from the linear independence of time frequency shifts, we obtain that, well, the coefficient of the identity operator is 1. So, and the coefficient of all other time frequency shifts here are 0. So in other words, we obtain the biorthogonality condition. So we start with a frame, apply the whole machinery, and end up with the biorthogonality condition. So that's one implication in this duality theorem. And to show you the equivalence, let's assume we start with the biorthogonality condition. We plug it in here and see, hey, this is just the identity operator. Okay, so if the biorthogonality condition holds, and we make sure that all these series here are well defined, so there is some cheating going on. So if we start with the biorthogonality condition, then we see that this sum here, sum of time frequency shifts on the operator level, is the identity. Well, if I have the identity, I apply to some f, take inner product with g, do the same on the other side, apply to some f, take inner product with g, and then I go this chain of identities backwards. I know this. I apply the fundamental identity of Gabor analysis and end up here. True for all f. So this means f possesses a representation of this form. And then you take into consideration that okay, here we need the Bessel assumption that this is a Bessel. This is Bessel, so that the 2 norm of f and the 2 norm of the coefficients are equivalent. But I think that in these few lines you can see the equivalence of the biorthogonality condition and the frame condition. And this is where I have to stop today. The biorthogonality is equivalent to resequence properties, is basically a formality. I can do that tomorrow. But I think I have to stop here. Thank you. Well, you said one.
Any question? So you said at the beginning that the theorem you're proving is due to, I mean, different situations, different authors. The Ron chain is more general. It's just not just that, or the one that.
Well, it's more. Well, let's say it's sort of the mathematics is hidden behind the language of fiberization. But essentially, that's Poisson's summation formula. They proved it for separable lattices, rectangular lattices.
But did they talk only about Gabor chapter or just general? Right.
That was. They saw the whole thing as a topic in the analysis of shift invariant spaces. Okay, you have this invariance on the translation. But this proof, first of all, it works for lattices, and it takes not just the partial invariance with respect to one of the operations, but this proof structure takes the invariance with respect to time frequency shifts simultaneously. Okay, I said you have to believe that, but I show you. So you write pi, let's see, zeta, pi, zeta inverse. Do that here. So you multiply pi zeta from here. No, let's write it the other way around. So multiply it here and here. And for this you have a formula. Okay? This is e to the 2 pi I mu zeta j mu pi mu. Okay? So you have identity is equal to this phase factor times this times this. So for all zeta, you have this representation. So should I, so sum gamma pi mu g, this here, this here. This is true for all zeta. So what you have is essentially an operator valued Fourier series in zeta that's constant. I believe, but little bit more. So one thing is to assume that both are. So this is summable, okay. The second thing is you to do this weakly. So you take FH here, FH here. Then you have something that's absolutely convergent. Then you have a plain, ordinary, absolutely convergent Fourier series that's constant. Okay? That means only the coefficient of the 0th term is non-zero and all others are 0. Yes, if you are worried about identities of operators, you go to the weak formulation and then you have L2 here, L2 here, so L1, so this is an absolutely convergent Fourier series. But let's say this is where you need the assumption that gamma is Bessel, so that this is really L2. This is where, so all these convergence issues I have downplayed, I haven't even mentioned them. This is where you have to do the homework. And to make, so this is a proof, and the question is, what kinds of assumptions do you need? But was that convincing?
Yeah. Yeah, please. What happens if you don't have an answer?
Well, then you are dead. There are no, except in one case, there are no characterization. Except for the Gaussian, there is no characterization of frame property by anything. There is some kind of duality theory, abstract duality theory by, let's see, Kasatsa and his team, and then by Ole Christensen. But they took them years to reproduce the duality for the lattice. And it's not clear what that general duality theory yields. I'm not sure that I understand the question.
It seems that this is like a basis for agent functions of some operator.
Mm-hmm.
Is it possible to formulate this in properties of some operator associated with this system?
So the duality.
Well, the keyword operator algebras, yes, you can put that in context of operator algebras. You look at, well, you look at the operator algebra generated by the time frequency shifts on the lattice. That's one operator algebra. Say you take the norm closure, And you look at the another operator algebra is the time frequency shifts generated by time frequency shifts on the adjoint lattice. And they're commutants. And there is a, well, one can make part of this here plausible by means of operator algebras, but the precise coefficients, I don't know. I can tell you a little bit more in the intermission.